So now the question is, why do teleports solve all our problems, right? So before, here is the equation we had from before. And in order to understand why the teleports solve our problems, we have to go back to the theory of Markov chains that I just alluded to in the previous lecture. So the way we define a Markov chain is the following. So Markov chain is this abstract mathematical object that has the following ingredients or parts to it. So first, we think that we have a set of states X. Okay? Then we have a transition matrix P, where Pij simply measures what is the probability that if we were at state I, how likely are we to transition to state J in a given time step, right? So Pij means, given that I was at J in previous step, how likely am I transition to state I, okay? And then pi is a stationary probability distribution of being at any of these states X. And our goal, right, is to compute the value of this equation, that pi equals p times pi, right? So this would be a stationary probability distribution of this Markov chain that is defined over a set of states and with the transition matrix P. And again, you immediately see the correspondence to our initial PageRank equation. Here we have pi equals p times pi, and we had r equals m times r. So theory of Markov chains says the following. It says that for any start vector, the power iteration applied to this Markov transition matrix P will converge to a unique positive stationary vector as long as this matrix P has three properties. It has to be stochastic, it has to be irreducible, and aperiodic. So now what I will show is that for each of these three conditions, stochastic, irreducible, and aperiodic, actually adding random teleports gives us in some sense stochastic transition matrix that has these properties. So what we will do now is convince ourselves that our matrix M, together with these random teleports, has all the three properties that we need for the PageRank vector R to exist. So the first question is, why do teleports make M stochastic? So a matrix is stochastic if its columns sum to 1. So in our case, or in case of dead ends, when we have this node M that has no outlinks, the column for node M did not sum to 1, it summed to 0, and the stochasticity condition for the matrix was violated. So now if we add this random teleportation that occurs with probability 1, we can basically think of this as adding the green edges from node M to any other node in the network, including the self edge, right? This means that our matrix M now got transformed, and our column for node M now has these values of 1 over 3 in it, so the column sums to 1, and we get the stochasticity property of matrix M. The way we can think about this in terms of equations is that basically we say we define a new matrix A, where we take our previous matrix M, and now I introduce two pieces of notation here. First, I have this vector A, where the ith component of vector A equals 1 if node I has out degree 0, if node I is a dead end, and otherwise it has value 0. And then this vector E is just vector of all ones. So it's a vector where every component has a value of 1. So what this basically means is we take matrix M, and wherever there is a column in the matrix M that has all zeros, we replace that with 1 over the out degree of that given node. Exactly what we did in the case of M. So this is what we did now, is basically random teleportations. What they do, they take our matrix M that cannot be stochastic if the graph has dead ends, and transform that into a new matrix A that is now stochastic by taking the teleportation with probability 1 out of the nodes with 0 out degree. So that's the first property. The second property is that M has to be aperiodic. So we say that a chain is periodic if there exists some value k such that the interval between two visits to some state S is always a multiple of k. So for example, if we were to have a graph on 3 nodes with a directed cycle, as I have it here, then, for example, this would be a periodic chain, because the random walk here is deterministic, and every 2 steps we return back to the same node. So by adding teleports, what this basically means is that that at any time we will be able to jump out of this kind of infinite loop, and we can even think that what we have is we have these self loops, so that the random walker can spend some time at a given node, and this way the periodicity is broken. And this is how basically random teleports solve the periodicity problem. Now the last property we need to talk about is irreducibility. And we say that M is irreducible when from any state there is a non-zero probability of going to any other state in the network. This means that basically we can never get stuck in a given state. So the way, for example, we would make our given graph here irreducible is to add all these other possible links, which basically means we would add random jumps. So this would mean that there is a non-zero probability of going from any state to any other state in our graph. So putting all this together, this is exactly what random jumps do. So basically, Google's solution to PageRank and to random surfer interpretation of PageRank was to introduce random jumps. So the idea is that we want to take matrix M, make it stochastic, aperiodic, irreducible. All this is achieved by slightly modifying our random walking process, where at each step a random surfer has 2 options. With probability beta, the random surfer goes and follows a random outlink, and with probability 1 minus beta, the random surfer jumps to some other page at random. So now what this basically means is that this now changes our PageRank equation. So if you think about the PageRank equation now, it's a bit different. So here, for example, the score of node J can be computed as follows, right? So basically what this is saying is the following. The importance of node J is first the sum of the importances of all the nodes I that point to it, where R sub I is the probability that random walker is at node I. Then we divide that by the out degree of I as the probability that the random walker will actually traverse the link towards J. And this only happens with probability beta, because the random walker, when they are at node I, has to decide to actually follow a link, and this happens with probability beta. And then, of course, how likely is the random walker to visit node J? It either does it by following a link, or with probability 1 minus beta, the random walker decides to jump. And if the random walker decides to jump, then it will land at a given node J with probability 1 over n, where n is the number of nodes in the network. Right? So basically we took our initial formulation of PageRank, and now we change it a bit, where we have the random walk part. This is the part where we kind of multiply with beta, and we have the random jump part, where we have the 1 minus beta. So now the question is, given this new random walk formulation, is power iteration still going to work? Right now we have a different, more complicated recursive equation. So the question is, how do we compute this? And the way we compute this is basically to run our eigenvector finding method, our power iteration again. The way we see that basically we have the same problem as before is to notice the following. So we have this, what we will call Google matrix. We will call it A, and we will express A as a matrix M plus some other matrices. So we take our matrix M and multiply it with beta. This is the part that comes due to random jumps. And then what we want to do is we have this other part, 1 minus beta, that basically this is the probabilities or transitions due to random jumps. And simply the expression we get here is that this is 1 minus beta, 1 over n, where n is the number of nodes in the graph, times the outer product of this vector of all ones called E. Okay? So what this means is that even with these random jumps, the PageRank solution can be expressed exactly as we had it before, that R equals A, now this is the Google matrix, not the matrix M anymore, times R. Of course, one question that we need to answer is, what is a good value of beta, right? How often should the random walker jump? For example, if beta would be 0, then what would that mean is that the random walker jumps all the time, so all the nodes in the network have exactly the same PageRank score, because the random walker is not really walking over the graph, it's just randomly jumping all the time. If we set beta to be equal to 1, then basically there is no random jumps, and this means that our matrix A wouldn't be stochastic anymore, and so on, and we would have no random jumps, and PageRank wouldn't really work. So what turns out is that the good value for beta is to set beta between 0.8 and 0.9. And usually people set beta to be 0.85, which basically means that for every 5 steps, you do a random jump. So a random walker, in some sense, on the average, would do 5 steps and a jump, another 5 steps and a jump, and so on. So that's basically the idea. So let's now see how this PageRank formulation would work in real world. So imagine we have our old graph as we had it before, 3 nodes, and in this case, node M is a spider trap, right? There is this self loop. What I also have on this graph is I have these green edges. And these green edges, you can think of them as edges that are there due to random jumps. So we have our matrix M as we had it before. With matrix M, everything is fine. It's still stochastic. The only problem is that node M is a dead end. Oh, sorry, is a spider trap. And now what I also did in this graph is I labeled every edge with its transition probability. So the way we do now is we take this matrix M, we take this other matrix of 1/3 and multiply it with 1 minus beta. So in this case, we are assuming beta is 0.8. And this gives us the matrix A. And now, if we do multiply our R with matrix A, this is how using power iteration, these are the different versions of vector R as we keep multiplying. And at the end, the PageRank scores we would converge to are given here. So basically, the score for node Y would be 7/33, for node A would be 5/33, and for node M would be 21/33. So what do we see? We see that M is still the most important node in the graph because of this spider trap, but we see that nodes Y and A have also non-zero score, and actually node A is more important than node Y. So it seems everything works and everything is fine.